All right, did that come up? Okay, good. Thank you very much. Appreciate your letting me participate in this conference. I'd like to share some more recent results that I've gotten on some work trying to model the actual dynamics of what's happening when the protons reach the the lunar grain surfaces. And I really appreciated the previous talk by Andrew and the talk this morning by Bill Farrell. Gave a great introduction to this subject and the importance of sputtering and the protons in the formation of the hydroxyl. This work was done in collaboration with Michael Poston, Thomas Orlando, Carl Hibbets, and Darby Gaia, members of our laser. To briefly recap, the M-cubes, this publication by McCord in 2011 showed the reduction of the M-cubed data for the 2.8 micron signal at the moon, which showed this bowl-shaped dependence, which is depleted at the equator but is increased at high latitudes. Now, the equator, of course, receives more solar wind flux than the poles. It goes roughly as cosine of theta. The equator is much hotter than the poles at noon. Experiments have shown that proton implantation is proportional to fluence up to saturation, but yet the moon shows OH lowest where flux and temperature are highest. This suggests that either an active process is removing OH at a rate competitive with implantation, or there's some other thermal effect in the material that's affecting the propensity for proton trapping. Now, Andrew just gave an overview of some more detailed modeling on proton irradiation and implantation, but just as a very simplistic picture, protons penetrate through a material and they lose energy as they decelerate, and they tend to deposit at the bottom of their track. This track's not very deep at solar wind energies. It's just a few atomic layers in most cases. But as the proton penetrates through the silicate lattice, it ionizes, it generates secondary electrons, and it leaves holes where chemical bonds used to be. These broken bonds in the silicate network constitute highly reactive trap sites. They're often either charged or have free radical character, but they're places the proton creates places where the hydrogens can later trap. So using these concepts to kind of construct a simplified mathematical model, I have indicated here the reaction where protons come in and combine with one of these newly generated traps that it's created to form a silicon hydroxyl. So to put this into mathematical terms, the rate of OH growth is proportional to both the flux of the protons and the trap density. So at early times, there are lots of traps available. So the implantation form OH is very rapid at early times. But we know that there's a finite limit to how many traps can be formed. So to include the effect of saturation, I've used a limit for how many traps can be generated. And this comes from experimental data where protons were implanted up to the limit where they reach saturation, and the densities from infrared measurements were able to extract what this limit is. So this equation just describes the source, the material loading in this equation. Now we go on to add processes which may deplete the hydroxyl in order to try to explain the observations. So what I've included here is a second process where the OH in the silicate lattice combines somehow, as yet to be determined, to release the hydrogen that it traps, and also to regenerate an available trap site. If it doesn't regenerate an available trap site, the reaction would not be reversible. So this must be the case. Now, the form that the hydrogen is liberated in is not determined here. It could be as H atoms, it could be as H2, it could be as water. We'll come back and address that question later. So now to put this into more mathematical terms, I have included with the source kinetics, I have two loss terms. The first one in red must be a function of either flux of solar wind protons or ions, temperature, and probably depends on the depth within the grain that the radiation penetrates to. The second term in green is a function of temperature, which I left out there, solar wind proton flux, solar UV flux, but I have it localized is z equals 0, representing surface localized processes such as photodesorption or surface thermal recombinative desorption. Now I've added an additional term to account for the z dependence on the loss term, which is a transport. And I've written it here in a form that indicates that we can include an anisotropic diffusion coefficient, which I have done to try to see if there was some radiation enhancement of the rate of diffusion toward the surface to give balance between the F term and the G term. But the most important thing is that this illustrates that the diffusion rate depends on the shape of the distribution. So it cannot be estimated because the gradient of the OH distribution can greatly affect how fast the OH is diffusing, independent of what the value of D itself is. So if I momentarily go back and just ignore the Z dependence, the equation is exactly solvable, and it allows us to parameterize these loss functions based on observation. Now, if I assume a purely thermal loss function, which is something like recombinative desorption, I can extract out an effective loss activation energy, and it's only 22 kilojoules per mole, which is very small for most chemical reactions and far smaller than any laboratory measurements of recombinative desorption that we suggest that we film not a likely mechanism. So sputtering must be operational here. But the form in which we can include the sputtering term is variable. We can adjust its functional shape. But if I include a loss term which depends on flux of solar wind protons and temperature, combined thermal radiation model, I get an even lower activation energy because presumably the radiation deposits energy in the surface and effectively is another source of energy for chemical reactions that then lowers its true temperature dependence. So to look at our results, first here plotted is my results for the first 100 lunar days. You can see the accumulation of OH. This is for latitude 0, the equator. The oscillations in the data are diurnal. The growth of the OH is rapid at early times, but it doesn't quite reach a steady state in 100 days. But it does decelerate the rate of implantation. This rate is comparable to the rate of OH diffusion, as I'll show you later. If we look at a zoom in of just the last few lunar days in this graph, you'll see that there's important structure in the variation of the OH as we go from dawn through noon to dusk. So at dawn, you can see that the OH actually starts to pick up and grows. This is because while the temperature is still cool, solar wind protons are starting to implant, and the rate of implantation is beating the rate of loss. However, as we approach noon, the temperature goes much, much hotter, so the rate of loss now starts to outcompete the rate of implantation, and so the net OH is actually depleted. But then as the surface cools off, we can see that the protons begin to accumulate again, and then through the night that level is frozen in. So this predicts that the dark side should have a fairly constant level of OH, whereas the day side would show the depletion. Now, if I compare back to the latitude data of the 2.8 micron, when we include this effective diffusion, we see that this gives us a fairly strange-looking prediction, which doesn't quite match the observations. At high latitudes, at the point labeled 1, the signal drops near the poles. This is because in the implantation volume where the protons are capable of reaching, they reach a saturation limit, and no more protons can enter. So the amount that can deposit there is limited. At the peaks of this sort of double peaked curve is where loss is still slow because the temperatures are cool, but diffusion is beginning to take an effect. The diffusion is allowing the OH to migrate inward into the grain at a rate that allows more protons to implant. It depletes the saturation region, so protons can continue to enter because some of them are moving out of the way deeper to the interior of the grain. But then at 3, it does, in fact, reproduce the low latitude data. And so here is a depth distribution of the OH at the equator shown on the right, and it's compared to some depth profiling measurements on actual lunar regular samples. And you can see there's a qualitative. Yes, ma'am.
You have about 90 seconds.
90 seconds. Okay. So the salient features here are the diurnal variations are showing up here in the fluctuations at the height. But you can also see the diffused OH entering into the material where it's being protected from surface losses. And notice the OH concentration at the surface is always very small. This means that surface localized loss processes are always diffusion limited. So no matter, at some point, no matter how strong those loss sinks are, they will never be faster than the rate that OH can be brought to the surface to be subject to them. So there's a limit to how important surface recombinant desorption or surface photodesorption can be. So here are these results plotted over a spherical map, and you can see that there's this center line here is the noon time. You can see that there's a dawn-dusk asymmetry, as I pointed out previously, and you can see how the OH intensity grows toward the poles, but then drops to zero at the actual north and south pole. And this shows some qualitative similarities to the epoxy measurements too. This is an This is a graph showing the difference between the equatorial proton distribution and the high latitude proton distribution. The biggest difference you can see here is that at high latitudes, the deposition region where the protons are implanting reaches saturation, and so no more OH can form. Whereas at low latitudes, the OH concentration is low. Diffusion carries it inward. The total amount of OH in the brain can grow basically limited, so that well, let me show you. So that the loss rate at the equator eventually is going to be beat out. In other words, because chemical reaction rates depend on concentration, not on total amount of OH, the concentration at the equator will always be low, even though the total OH there is unlimited due to diffusion. So equatorial OH will always essentially be higher than at the poles if considering only chemical loss mechanisms. And like I said, because the 100-day didn't reach convergence, I let it run out to 1,000 lunar days, and this, in fact, agrees with what I just said, that eventually the equatorial OH catches up with the polar OH, because the equatorial grains, because diffusion rates are operative there, they can eventually accumulate larger amounts of OH than the poles can. So this means that something else is missing. There must be an alternative loss mechanism. It could be grain turnover, exposing fresh grains and burying the mature grains, micrometeorite vaporization, or heavy ion sputtering, but which aren't included here. There must be some other loss term besides chemical rate. So just a few conclusions here. Because the diffusion rates depend on the gradient of the OH, it has to be simulated. And the diffusion inward protects the OH. So it requires by deep loss mechanism, I mean one that's operational even within the subsurface of the grain, because surface localized loss processes alone cannot deplete OH faster than it's being implanted. And that's because of the limitation of diffusion. And you can read a few more of these conclusions there, but I'll be happy to entertain any questions you have.
Great, thank you. And as we're getting to the questions, can the next speaker please start setting up, sharing screen and all that?
Okay, so Larry had asked a question which Dana answered. I asked a question which I don't think makes any sense now that your talk is over. So I'm going to move on to one from Gordon. Don't you think that potential per cold traps and migration to polar cold traps and migration to polar regions fill in your hydrogen hole at high latitudes, as most neutron observations show?
Oh, absolutely, yes. At high latitudes, it becomes more difficult to discern the 2.8 and the 3 micron band in the observations, and it's quite possible that the signals are leaking into each other's channels, and exactly the water or whatever volatile that may have migrated covers that hole, and that could explain the discrepancy between the model and the data.